Okay, class, picking up where we left off at, we ended up with the answer 1.286 e negative 4, and we know that actually means 1.286 times 10 to the negative 4. Or we could write that in this decimal format, which is 0.0001286. And this is the final answer. Now, scroll on over to the next page. It says reconstructed probability models before by using a tree diagram. The multiplication rule for independent events is a different, better way to calculate probabilities because it doesn't assume equally likely branching the way tree diagrams do. It can be used for large sample spaces. Tree diagrams are a nightmare. Example 5. We have multiplication rule when outcomes are not equally likely. You have a loaded, non-fair coin that would toss heads 75% of the time. You are going to toss the coin twice. Assuming the coin tosses are independent of each other, find the following probabilities using the multiplication rule for independent events. So we have the probability of 2 heads. So this is the same as saying the probability of heads times the probability of heads. And the probability of heads is 0.75, because remember these are loaded dice, and 0.75 multiplied by each other. So your final answer would be 0.5625. Now we go to the probability of heads and tails. So it would be the probability of heads times the probability of tails. The probability of heads is 0.75. And the probability of tails is 0.25. And when we multiply this out, this gives us 0.1875. Now we have the probability of tails and heads. Probability of tails times the probability of heads. And we will have 0.25 times 0.75, which will result in the same answer as our previous problem, 0.1875. So it doesn't matter the order here, it's coming out to be the same answer. Now we have the probability of 2 tails here. So we have the probability of tails times the probability of tails. Tails is 0.25 probability and 0.25. And this will give us 0.0625. Now remember, I have to stress that these are loaded coins, so you have to be aware of that. Okay, now we come here to E. It says use the probabilities found above to construct a probability model for the experiment. Verify that it meets the requirements of a valid probability model. Okay, first of all, we had 2 heads. We had a head and a tail. Then we had a tail and a head. Then we had 2 tails. So the 2 heads was 0.5625. The head and the tail was 0.1875. The tail and the head was 0.1875. And the 2 tails was 0.0625. And their sum was equal to 1.00. Well, 1.000. So this does verify to be a good probability model because the total amount of a probability model must equal 1 or very close to 1. So that is our final answer. So it does prove it. Okay, now we go to example 6. Multiplication rule when the sample space is large. You are going to toss a coin 10 times as a probability experiment. If it is a fair coin, what's the probability of getting all heads to 6 decimal places? So we have the probability of heads 10 times. So we had a probability of heads, and we would take that to the 10th power. Probability of heads is 1/2. Take that to the 10th power, and that would give us 0.000977. And that is our final answer. Now we go here to B. It says if it is a loaded, non-fair coin that would toss heads 75% of the time, what's the probability of all 10 tosses showing heads to 6 decimal places? So it would basically start off the same here. So the probability of head 10 times, and it's not fair. So that would be the probability of 0.75, because that's the value of the not fair head. And we would take that to the 10th power. So that would be 0.75 to the 10th power, which is equal to 0.056314. And that is the final answer. Now, we move on to the last page, which is example 7. And it says the following involve a standard 52 card poker deck. Part 1. You are going to select 2 cards at random with replacement after each. Now you know when it says replacement, that means that when you take the card out, you would just write down what it is and then put it back and then do another selection. So you're never without 52 cards. Okay, so we have A. How large is the sample space? Okay, you had 2 selections. You're going to have 52 cards for the first draw and still 52 cards for the second draw because you are replacing what you took out. So it'll be 2,704. And this is how many possible outcomes you can have. Okay, now B. It says find the probability that the first card is a face card and the second card is a spade. Now we had a probability of face times the probability of a spade. Now we know the probability of a face card is 12 face cards out of the 52 card deck. And spades is 13 spades out of a 52 card deck. And when you multiply this out, this gives you 156 over 2,704, which would basically give you an answer of 0.05769. And this is your final answer. Now, we come here to C. It says find the probability that both cards are queens. Okay, so now we have a probability of a queen times the probability of another queen. Now, there are 4 queens in a deck of 52 cards. So this would be 4 over 52. And since we're replacing it, we're putting it back, it still would be 4 queens out of 52 cards. So this will give you 16 out of 2,704, which will give you 0.00592 once you multiply it. Now we go here to part 2. It says you are going to select 3 cards at random with replacement after each. So D, how large is the sample space? So this time, since it's replacement, we'll do 52 times itself 3 times. So that would give it 140,608 outcomes, possible outcomes. Now E, it says find the probability that all 3 are queens as reduced fractions and a decimal. So again, we know that it's 4 queens in a deck of 52 cards. We only have to take that to the 3rd power. So that will give us 4 over 52 simplifies to 1 over 13. We take that to the third power, and that will give us approximately 0.000455. Now, if you put in your calculator, you will get 4.55 e to the negative 4 here. So either one would suffice. Okay, now we go here to F, or part 3. You are going to select 50 cards at random with replacement after each. Now we're dealing with 50 cards now instead of 52. Okay, how large is this sample space? So it's 50 cards. So we'll do 50 actually it's not 50 cards. It's still 52 cards. But they're saying of these 52 cards, you're going to select 50 at random. So you would take 52 to the 50th power, and that would give you 6.312 times 10 to the 85th power. Or in your calculator, it'll come up as 6.312. And then it'll be E and 85. So you can write it as either or. If you put 52 to the 50th power in your calculator, it'll come up as this, and you can rewrite it as this here. Okay, now it says find the probability of selecting a queen for all 50 random picks. So we know a queen is 4 out of 52, but we'll take that to the 50th power. And if you put that in your calculator, it'll give you 2.008 e negative 56. Now, if you don't have a calculator and you did this, well, if you don't have the TI calculator, typically it won't show up, but you can rewrite this as this here if you so choose, showing the times 10. Okay, now for H, explain why we cannot just say the probability you found in part G is 0. Because it is still possible but extremely unlikely. Now, here's the thing. Even though it's extremely unlikely, remember 0 means that it's impossible. It cannot happen. But there is a probability, even though it's very, very small, that this could happen. So that is why we cannot say that part G is 0.